Hey everybody, Norm here. We're on to Project Euler problem number 4, and I think I'm finally starting to realize how poorly I'm probably going to do at this one in terms of just understanding like what Project Euler is aiming to do from the standpoint of a recreational mathematics. And it's not necessarily a failure of LabVIEW, but it's more, I've never really done recreational math. And so there are certain things about what I'm learning, what I'm finding out, that just, well, yeah, it's just getting harder for me to realize that really the essence of what Euler did. Now, for those of you who don't know, Euler, one of his claims to fame is when he was a young student, a teacher was looking to cause the students to spend more time so that the teacher could relax and have the students add up the numbers from 1 to 100. And as the story goes, young Euler decided, hey, instead of adding up all the numbers 1, 2, 3, all I need to do is add 1 and 99. It's 100. Add 2 and 98 and 3 and 97. And you get the idea. He very quickly discovered there's a very simple pattern that turns into how to simplify the math to basically make the math easier. And what I'm finding out as I'm doing some of these puzzles in LabVIEW that I can do them brute force, but many of these challenges are in order to try to figure out how to simplify the equation. So in this session, I'm going to obviously still go through the brute force approach. I'm going to show you what I did. Hint, hint, I've already gone through and done it once, but we're still going to walk through what I'm figuring out as I try to implement this. But I'm also going to see if I can record a little bit more and actually walk through figuring out how we possibly could optimize this by using LabVIEW to do the visualization of some of these numbers and see what comes from it. All right, so with that, let's go. All right, so we're starting off here back on the Project Euler page. We're going to go to look at this from the standpoint of number 4. So if we come in here, it says a palindromic number. And so that's the number that reads the same both ways. Obviously, this is the example that they give us. And so what they're doing for is they're asking for more factors again. And so if I sorry about that, let's zoom out. The largest palindrome named from the product of two two-digit numbers is 91 and 99. And so obviously that's just, you could calculate all of the possible numbers, brute forcing and go from there. And so I never know which one of these brute force approaches is going to be particularly difficult. But I realized all right, I need to figure out the factors of a palindromic number so I could kind of go through all of the numbers basically from 0 to, well, Lord knows what the largest three-digit number is, basically 999 squared, if I'm not mistaken. I could calculate those and go the other direction, but I didn't quite do that. But the twist is I knew a little bit of what we were trying to do was simplify because it's giving us this idea of 2 3-digit numbers. And so we have a obviously the numbers 0 through 99 are not going to be applicable. So we can already start to think of a little bit of ways to optimize this. So let's go ahead and give it a go. So on a diagram, if I know that I needed to come up with all of the numbers greater than some value, and this is just kind of a design pattern, there's a way that typically you'll see people do it is they'll use a for loop, and they will just take the indexing numbers off of the for loop and go ahead and wire that in right there. And so if I needed to have between, of course, 0 and 900 or 999, I could just go ahead and put right click there and create constant, and then put 1,000 numbers in there. And then I would go ahead and make sure that it gives me what I want on the output side right here. Using some of these new features within LabVIEW where I can, once again, I think I noted in an earlier video, start wiring, right click, and then I can go ahead and create an indicator. Same thing as I was doing up here for the constant. So if I go ahead and I run this, I can do that again. I can show another thing with the arrays. I just want to see the values. I'll make it vertical scroll bar, and of course I could go ahead and scroll through these values right there. Nothing too grandiose. You get the idea that I've gotten all my numbers there. Quick note is that this value here that we're seeing is the index, but it's the index of the one displayed kind of at the top. So 93, 94, 95, you get the idea of what we're seeing in here. So this is giving us all of those values, but already we don't need part of this. And so what do we need to do? Well, we can exclude all values, or we can start in 0 index higher. So I'm going to go ahead and use that feature of LabVIEW that I like, which is the expression node. And that allows me to kind of have some very simplistic math and kind of a a C-style convention without having an extra primitive and then a constant on the diagram. I can do x plus 100. So therefore, my first value is going to go out there. And of course, I'm going to remove this and move this down to 900. Now, if I wanted to do this more scalable, obviously I would want that to be more of a primitive, but we're going to go ahead and run that right here. And now we have basically all of our 3-digit numbers going from here to there. All right, well, that's fine. So that math is fine. And so now we know that we need to do this again and again. So we can kind of, once again, brute force this a little bit more. And I'm going to go ahead and multiply this times another one where I'm going to do for structure. So another neat thing to note while doing this run right here is that within LabVIEW, you keep seeing me probably bring up Quick Drop, which is a great tool if you know what you're looking for. But if you don't know what the shortcuts are that I'm using, it's kind of, you have to know the exact name, which is good. But there's a lot of ones that are very, very frequently known. So if I were to go to a let's see if I can look at it here. You can scroll down. Yeah, some of these are just known. They've been created for us. But if I look for something right here, like for loop, that has FS. And this was done by a friend of mine, Darren Nattinger, here at NI, that he tries to keep, most LabVIEW developers keep their left hand on the keyboard and the other hand, the right hand, on the mouse. And so a lot of these shortcuts are all so that you can keep your left hand not moving back and forth across the keyboard, and you don't need to use your right hand to touch any keys on the right side. So instead of typing in for loop, you do FS for structure, and then you've got a better, like you have what you're looking for very quickly. Same thing, actually a couple different ones right here. Flat sequence structure is another one that I typically use. What's some other event structure, EVSTR. Once again, these are ones that the LabVIEW aficionados of the world have figured out over time are particularly useful. And so we've already pre-canned a variety of them for you. But maybe the more important thing here is if you do something very unique in your field that's very, very helpful, like I do a lot of complex math. And so for me, if I wanted to do something like complex conjugate, so I don't have that as a thing. So if every time I wanted to do complex conjugate, I don't want to type in complex conjugate, and I don't want to have to navigate all my palettes. So I can just go here and type in CC and add that cluster constant. Okay, well, that's fine. So let's go ahead and, or they'll do CCJ. Conjugate. Yeah, that works. CC, great. CCJ works. And so now if I just do CCJ, now I can have complex conjugate on my diagram. So they give you the ability to customize this. And if you don't know what's available, you can go ahead and scan through that list. Or even just as you bring up Quick Drop, a variety of them that have been loaded, you can see here that the name will show up there. So if I typed in complex to polar, you can see the shortcut name listed there and the longer name in the parentheses that are available, hopefully giving you a little bit of need, but I guess. So now that I know that I've got these two, I could theoretically speaking build an array from 0 to 999 and another one from 0 to 999, take that larger array and then start to pull out which one's palindromic in nature. But I'm going to go ahead and do it within the same structure. So a bit of a nesting of the for loops that we've got here. And I'm basically going to create X. There we go. So now I've got that in there. And so now what I've got through is I'm multiplying the index to do that same math here. X plus 100. And now what I can do is calculate each one of these on the fly and see, is it indeed palindromic? But how do you take a number, and actually let's go ahead and delete those things right there. How do you determine, is a number palindromic? Well, there's a few different ways you could possibly do this. And one of the ways that I know is my brute force way is I can very quickly, you can't reverse the numbers, and there's no mathematical operation to reverse numbers, but there is a string operation to reverse strings, or you can reverse an array. So in my case, I'm going to go ahead and leverage the fact that each one of these characters is a principal character. And so I'm going to do number to decimal string, because I know these are all decimal values right here. And so let's go ahead and take the factor of those two 3-digit numbers. I have a string. I'm going to go ahead and reverse string. Actually, let's go ahead and do it through the palettes this time. I'm going to go to the programming palette in the string. Once again, it's a really good thing. If you've never really walked through all of these folders and functions, we've tried to make it very, very easy for you to do that, to discover what's available. Sorry, I'm dragging some of this stuff off the screen here. And so if you don't like the way that it looks, guess what? You can actually change the way that your palettes are being viewed at the moment, either temporarily or permanently from LabVIEW tools options. So this is something that you can do. You can even view it as I think you do as like a tree. Yeah, so this is another one if you really like this style of view of functions that are available, but most of us in the LabVIEW community will end up using use icons or icons in text. I haven't used categories for a while. Yeah, that's right. This is another one that typically comes up. But I'm going to go ahead and go to icons in text, programming, string. Another nice thing to note in this is that if for some reason you resize this in an awkward way that you don't like, if you click on this little glyph right here, it will resize it to kind of the default intended size for that palette. So there we go. Now we've got string, and then I'm going to look for the reverse string, which is in here. Let's go to the additional string functions. There we go, reverse string. So we've got that there. We also have the ability to rotate the string, a lot of different things that are going to be particularly handy. So let's go ahead and get that reverse string in here. We're going to go ahead and equals. So we're going to, where's the equal? You would go to the comparison palette. And so I'm just going to do the very simple equals right there. So now what we've got is, hey, is this number indeed palindromic? So what I'm going to do is I'm going to take this, I'm going to wire these through. And I'm also going to do something that we've seen in the other examples here, where if this works right here, I should be able to right click and change the tunnel mode to, you're going to have it to be conditional. And so when they're equal, we're going to go ahead and build up that array. And then the other thing, which I don't know if I've noted in other videos, is where I have the ability to take, this is like if I were to just create an indicator off of this, it's going to be a two-dimensional array where each row is each array that comes into it. So yeah, for those of you still getting used to LabVIEW, this right here is based on the thickness of the wire, is indeed a scalar value. And this is an array of scalar values, and then this is an array of other arrays, in other words, a two-dimensional array. But really what I want to do is I just want to kind of build them all out and just have them be present and available there. So once again, I don't need it as a two-dimensional array. I just need it as really my desired end data type is a one-dimensional array. And so instead of doing that, I can change the tunnel mode to concatenating. And what that will do is it'll take an array and it'll just kind of add more onto the end of the array. And the same thing is actually possible with strings now in some of the newer versions of LabVIEW. So what we have here, let's go ahead and create that as an indicator. I'm going to go to the front panel there, let it run. Oh, and we're missing some things here. All right, we've got it set here. We should be able to run this. We're missing the number of iterations, so we're going to start running that from 99. Let that run, and voila. Now all of a sudden we have the ability to see all of our palindromic numbers, but they're not. How do we find the largest one? Well, this is another great little feature that is in LabVIEW within the array capabilities. It's actually within the comparison palette. Let's go ahead and see if I can zoom in on this again here. And I stand corrected. It's not the comparison palette. It's underneath the array palette. But you have the ability in the array to go ahead and extract the maximum and minimum from that array. So once again, it's kind of like the standard library in C. There's just a lot of stuff. And once you know all of them, you're pretty darn dangerous and you don't need to recreate everything from scratch. And so this is once again a great little feature that we've got in there. Drag that maximum value out and let it run. 90669, that looks like a palindromic number by nature to me. So as you can see right there, if we go back to the web page for this, indeed, the answer indeed is 906609. So not all that too surprising. It seems like a pretty simplistic problem, and indeed it was. The code didn't take much to go ahead and get functional here. We used just a few of the given features, but what we want to do is say like, all right, so what is inefficient about what we've got here? And so sometimes some of the ways that you can figure out if things are effectively inefficient is you can kind of look at the data set, look at the size of the data set. And even in some of the things I've done recently, just looking at the diagram itself, not what this is an example, but recently just looking at the layout of it and realizing how I can reduce the equation effectively, but reducing it in a programmatic way. Now, one of the things that we can note with all of this here is that very, very clearly we're calculating many of the same values twice. And that's very, very inappropriate. So how many values are we looking at overall? Like where is the distribution of all of these values, and how would I possibly even determine, like, are there duplicates in here? And one of the interesting ways that we can go ahead and actually do that very operation is by using one of the newer features in LabVIEW of sets and maps, or underneath the collection section underneath programming right here. Now, one of the unique things for anybody that's ever worked in databases, the idea of a Venn diagram, or joins, inners, and outers, and is it part of a set? Well, mathematic as well, right? The idea of values are part of a set, or all set of valid integers. Well, what we can do is we can actually compare how inefficient we are to some degree in here. And we're going to leverage the set capabilities. And so what we're going to do is we're going to insert all of these values into a set, and then we're going to extract all the values out on the other side, just to see, what's the word I'm looking for? How many are now missing. And so if we were to go in here, we can take the insert into set. I'm going to take the element that's in there. Now it's taking the array as the entire element, and I don't want that. I really want to index into that set every one of them. So I'm going to go ahead and do that, and I'll change this tunnel into a shift register, replace with shift register that you saw there. So one of the things that you can see now that we're doing is, now that we're starting to add an element into a set, but we have to give the input to that set a data type, or the set that already existed. So the order of creation of some of these things is you define the data, you take the output, and then you set the shift register, and then it sets the data type. And so for this, I'm going to give the shift register, which is basically a variable in a loop at this point, kind of a loop sensitive or loop local variable. And I'm going to create a constant for it up front so that it clears that variable every time the program runs. And now what we should be able to do is look at the array size of the before and after of all elements inside of that set. So once again, the code's a little sloppy here, but we're going to go ahead and get things out of it. All right, convert set to array. That's actually a primitive. That's actually a merge VI. That's another neat feature of LabVIEW, is that you can actually have things on the palette that don't drop as a single node or as a sub VI. You can actually have it be an entire chunk of code, and the block diagram from that code will show up. If you ever wanted to learn more about that, post something in the comments. Let's go ahead and learn together. But what this does, gives us the ability is to, right there, very simple. Now I have taking the advantage of the syntax of LabVIEW, where you can take a set into a for loop and get all of the values out of it on the other side. So let's go ahead and get that array size over here as well. And let's just go ahead and create indicators for each one of those. And now we can kind of compare those two different sizes, both the before and afterwards. All right, so you can see there is a way too many values that we are comparing in this overall set. And that makes a lot of sense, because we're basically multiplying. If I were to kind of draw on the screen here, right? If we had all of the 1, 2, 3, 4, 5, 6, you get the idea. We're going to do like what Euler did. We're going to simplify to something a little bit easier, right? We're multiplying 1 times 2 and 1 times 2. So there's like this entire lower section that we don't have to calculate yet again. And so that is one way we could simplify the amount of effort spent trying to calculate or find the palindromic number. So, and another thing, if you've gotten engrossed in this, if you've gotten engrossed in any of this, the Euler project capabilities that we've got, one of the things that you'll see if you are doing and following along at home is that you can download an overview of the problem once you kind of get that. And this is so very important in terms of your learning, because this was like, oh, these are the clever ways that you can reduce this problem yet further. All right, so and then of course this is all showing it in terms of text, and it's showing you how simple the code can be or how complex it is, and so you'd have to read through this one. And it, once again, it's, if you like reading text code, that's fine. It's a bit of the brute force way of determining this one, but it also goes through and helps you understand a little bit of, let me see if I can get here where it actually breaks the number apart. This is one of the most interesting ways of doing it is if you were to break the final number, the palindromic number of p apart into its constituent components, it's very clear that the first digit is 100,000 times x, and that will match x on the end. Similarly, so you've got 10,000y times 10y, and then you kind of reverse stitching together the number, and you can kind of come up with, or you can't kind of, but you do come up with a very elegant little equation there, or a reduction, for which I still have no idea. If anybody's in the comments still watching this and you know how they knew that 11 was a multiple of each one of those numbers, please let me know. I have no clue. I searched AI and in between, nothing made sense. Now, funny enough, I say this, but at the same time, if I really wanted to, I would go to the thread in the forum. And so Euler Project, interestingly enough, if you like recreational math, not just learning computer languages, you can go to here and you can see other people's solutions and questions. And so if you want to know this, or you want to see if I actually did it, go ahead and look there in problem 4. All right. So we are a little bit long in the tooth. We're coming up on that 25-minute mark, and that's probably about as far as we should go in this. I think let's go ahead and review some of the things that we talked about in the language itself. So the things that we ended up covering were a couple different structure types. We talked a little bit about the expression node. I think I may have shown that in a previous video for entering in very simplistic mathematical equations to kind of do some simple things. And of course, if you want to know deeper about how far that simple script can go, right click on it and look at the help. It allows us to go ahead and see the very simple operation to take a number and turn it into a string. The fact that we have a string operation to go forward and backwards and reverse those strings. And once again, advocating for you to go ahead and look through your palettes. If you're unfamiliar with what's available there, we took a lot of time to arrange them in a logical way so that you can discover and take advantage of the work instead of recreating how to reverse a string. We talked a little bit about the polymorphic nature of our functions. Now, once again, an equals is probably the worst example to talk about how polymorphic it is, except when all of a sudden it turns into much more complex data structures that it can still go through and determine some degree of equality, or actually compare individual elements of an array as well. And it's once again, there's a rabbit trail with that one. But it's not just the equal, it's many of the primitives of LabVIEW will auto-adapt to the data type in an intelligent way. So take advantage of it when you can. And the other one that is probably the brand new feature, that's probably the newest feature that I've noted, was the inclusion of sets and maps. And what we showed off was the idea of a set. And you can do, you can query a set to see if something's inside of it or outside of it. You can join or exclude. And all I did is I just used something very simple to just remove duplicates. It was, I could scan through that array and I could search the array every time to determine is something already in there. But I have an easy function. I have an easy button. That's one thing in LabVIEW called a set that can only have one of every unique type or every unique thing. And so I just put all of my numbers, tried to put them all into the set, and voila, the only thing that came out were all the unique ones. And so take advantage of that if you want to, and dive deeper once again into this. That's like an abuse of the set primitives and all the effort that went into making them fast and efficient, work on real time, and work on various different platforms as well as LabVIEW does. So one of the deeper features that usually beginners don't always gravitate towards was quick drop that we covered. And we went into that a little bit and we saw how there are quick drop shortcuts. So if you know what you're looking for, feel free to type it in. But if you want to type fewer characters, you can take it like for loop, you can go ahead and learn those shortcuts. You can either go to the configuration button on quick drop itself, or you can actually just type in what you're looking for and see if that thing that you're wanting to type in already has a predefined shortcut as defined by people that have come before you. So go ahead and take advantage of that. Another thing that we kind of dabbled in was the palettes and being able to not only navigate them, as I've noted, but the ability to view them in a different fashion. So you can actually have favorites. You can actually log things as favorites. We didn't even cover that. And then, of course, if things get, whatever view you want, as icon or whatnot, or list or tree, or even if you shape the window wrong, you can kind of resize that back to what you need and go from there. All right, y'all. So thank you very much for sticking around. Please leave some comments on the video here if you've stuck around to the end. It matters a lot so that I can make sure to focus either more on certain things or less on other parts. And I'll see you in Project 5. Thanks.